Hello, everyone. I'm Ripon Saha. I'm a grad student working with Professor Mark Broadwin at the University of Missouri, Kansas City. So today I'm going to talk about a very giant structure at Redshift 1.75. So by this point, you already know that the massive galaxy clusters we see around us today have evolved from a progenitor population called the protoclusters that people have been finding out to Redshift 6 and 7. And as you can see in the simulated image, that these protoclusters or clusters are not isolated structures. Rather, they're connected through low density filaments, and they reside in a web-like structures, in a network of structures. So to understand this process of evolution, how they evolve over time, we must understand the environment they're in. We must understand the network of structures they're in. So people have been finding very primordial supercluster structures recently, like this on the top left. This is a Redshift 5 proto-supercluster that has at least two protoclusters closely located to each other. And there's a Hyperion with multiple density peaks at Redshift 2.45. We also have similar examples with evolved extra-selected clusters at intermediate redshifts, like the Lynx supercluster, and also this is an HSC map of the 1604 cluster at issue point 9, where you can see lots of bright clusters with smaller galaxy groups and overdense regions. On the right top, you can see a recent addition to this sample size, where it's a collection of lots of extra selected clusters in a very compact region in the Eero-Zeta fields. And finally, we have our home Laniakea supercluster, where we have our Vargo local supercluster and also the Great Attractor and what's not. So how we have evolved from a very primordial supercluster stage to this giant Laniakea type of structures is a very interesting open question that we are interested in. So this is a very pretty recent picture of the galaxy clusters and protoclusters found, and we for our analysis we pick a very massive clusters at Redshift 1.75, which is IDCS 1426.5 that Stefano talked about earlier today, and we wanted to study this cluster and its neighborhood, the structures around it at Redshift 1.75. And after studying, we found that it is not only the massive cluster at Redshift 1.75, but it is embedded in a giant network of structures, or what we calling it is a proto-supercluster. And from an evolutionary perspective, this cluster or this proto-supercluster is located at a very interesting epoch, which can bridge the gap between this primordial structures and modern day evolved structure. As because we found that in these protoclusters, we have one mature evolved cluster and also lots of forming cluster. So in the following slide, I'll explain how we detected this proto-supercluster briefly. So a bit of background, as we know in the low redshift regime, like on the left, I have shown that if you look at the low redshift galaxy clusters in the cores, the star formation really drops. And if you go to the outskirt, the star formation really tries to catch up the field value. And this is what is also showing for a redshift 0 cluster collection separated by low density filaments. And on the right, it is showing that as you go move towards the cluster core from the filament, the star formation really drops. But when you go to the high redshift regime at 1.6 or 1.4 or 1.5, the scenario changes drastically. That means the star formation rate or the AGN fraction really goes up once you go from the outskirt to the cluster cores. This means that if you catch a star-forming galaxy or an AGN at high redshift, the chance of being it in the vicinity of a cluster is much higher than it is at low redshift. So what do we do to find higher shift structures at 1.75? We adopt a sample of 2600 dust obscured galaxies that are very faint in optical wavelengths, but very bright in infrared, and they are going through extreme star formation and AGN activity. So, so as I said, these are very infrared bright, and that's why they were detected in MIPS 24 micron in 24 micron. And from this value, you can see they are so bright in 24 micron that sometimes invisible in optical wavelengths. We have spectroscopic data for a small sample of this 2600 dog distributed over the entire field of booties. And from that spectroscopic data, we know that mean redshift of the dogs is 2 with a variance of 0.5. And this is the Buddhist field, and where a host of different objects have been found over the last decade. And this is roughly the location of the IDCS cluster and the proto-supercluster that it is in at 1.75. So as I said, a very small sample of these dogs are confirmed spectroscopically. So what we do is we use a machine learning code to compute the photometric redshift for the rest of the dogs which do not have any spectroscopic data. That's because template-fitting method fails because, as I said, the dogs are a mixed population of star formation and AGN activities. That's why it's very hard to do template-fitting method for calculating photometric redshift for these dogs. And to find overdensities, we select galaxies from the SeedWave survey, we identify galaxies that are selected in 4.5 micron, and we use typical template-fitting redshifts with high precision. And finally, we identify 40,000 galaxies at redshift 1.75 over the entire field of Woodies. So in which we will find the overdensities and at 1.75 using these dogs as a signpost. And the results are quite interesting. In this plot, I'm showing you at least 3 examples of the large-scale structures of the overdense regions or cluster candidates that we have found at redshift 1.75 with more than 4 sigma significance using the dogs, the extremely star-forming and AGN active population as a signpost. So on the top left, I'm showing an example where the yellow squares are representing the members at redshift 1.75 of this cluster, and the 2 green circles are representing the dogs that are signposting this structure. On the bottom left, it's another example where two dogs are signposting the same structure, and we also found an spectroscopically confirmed radio loud AGN that I have shown with a cyan circle right in the middle of the cluster at 1.75, and which is very common for high-Z clusters. And we rediscovered basically the IDCS clusters independently with our dog signpost method, and which kind of demonstrate the success of this thing. And finally, we found that these structures are not isolated. They are not far from each other, but they are part of a big giant network of structures. I'll slowly explain this plot to you. So these are the examples that I've shown in my previous plots. And as you can see, these are basically part of this filamentary network of structures. And the white dash circles are the dog signposted over dense regions. I'm sorry, the yellow dash circles are the dog signposted over dense regions with more than 4 sigma significance. The white ones are 3 sigma significant candidates, and the green dots are the dogs that are signposting this over dense regions. And the red stars are basically the spectroscopically confirmed members at 1.75 in this giant structure. And the background density map are the density map of the galaxies at 1.75, and the right color bar is basically a proxy for the excess densities in this field. So the lightest contour represents the region with no excess density, and the darkest contours basically represents the regions with most excess density. So but from this plot, it's quite impossible to understand whether the association is real or is just a projection effect, the association between the dogs and the overdense regions at 1.75. So I am using the photoz's that I've said I've calculated, computed using machine learning. And when I use that, I have pointed out that the dogs that are consistent at 1.75 with black circles around it. So as you can see that some of the dogs do not have black circles on them. That means either they are not consistent with being at 1.75, or they do not have the enough photometric detection in enough bands to compute the photoz's. So, but the good part of this thing is, almost with a few exceptions, we'll find almost every node, almost every overdense region has at least one signpost that is consistent with being at 1.75. So once you add the 2 sigma candidates, now it starts all making sense, because now you can see that all the overdense regions are connected via low density regions, which is very commonly seen is in a supercluster type of structures. And so even if you ignore the background density maps, the only dog signposted overdense regions shows you the distribution of matter in this giant structure, that shows you the elongated filamentary structures in this giant network of structure. So as you can also see, the IDCS has a YOLO dash circle. That means it is also, as I said, has been detected with a more than 4 sigma significance. We also searched for overdense regions using dogs on protocluster scales. And as you can see, we can also find overdense regions, and we can recover the same structure using protocluster scale search. But the good part about it is we did not recover IDCS. We did not find IDCS significant on protocluster scale, and that's probably because, and that's what we expected also. That's probably because IDCS is a collapsed structure already. So, but the rest of the overdense nodes are consistent with being a protocluster, and that's why we're calling it a protocluster, protosupercluster, because some of the nodes might be still in a forming stage, not like IDCS. So we also computed the autocorrelation function of the dogs in this supercluster field and compared the result with the rest of the Buddhist field. And we found that the dogs are more autocorrelated in the supercluster field and than the rest of the Buddhist field. And that's probably because of the presence of the supercluster. That means the dogs are more bright, more massive in the supercluster than the rest of the Buddhist field. So in future, we hope to understand what part of these superclusters, which of the nodes are going to collapse by redshift of 0 or in future. And I mean, given the size, it's very unlikely that everything will collapse into one single node. But we do want to understand from a theoretical perspective, that which of the nodes are going to be collapsed by redshift of 0, and we will be able to make an evolutionary connection between this kind of population and this kind of population. Thank you very much. That's all from me.